Hi everyone, I'm Peter Yoachim, and I'm here to give you an introduction to the Rubin Observatory Scheduler. This is part of the August 2020 Project and Community Workshop, so go ahead and check online if you want to come to our session. That hopefully you've watched this before the session. Let's get going. So the one-slide introduction to Rubin Observatory, formerly LSST, is that we have an 8-meter telescope on Cerro Pachon in Chile. There's a picture of the summit on the upper right. On this telescope, we're equipping it with a 3.5 gigapixel camera. There's a schematic in the lower right of our kind of SUV size and weight camera. And we're going to have a real-time alert stream. So on the lower left there, you can see the path the data takes from Chile through fiber optic cables, up to Florida, up to Urbana, where images will be processed in real time to give out alerts for everything that changes in the sky, all the asteroids that move, all the supernovae that explode. And our goal is to kind of make a movie of the sky and capture a lot of the time domain science in astronomy. But that raises the question, where exactly should we point the telescope? We've clearly got the hardware to make a movie of the sky, but we want to make the best movie possible. So, our motivations for the scheduler. We have a science requirements document that gives us some pretty hard constraints on what we need to do. So in that document, it says we need to cover an area of 18,000 square degrees and observe every point in that 18,000 square degrees 825 times over 10 years. There are also requirements on the precision of parallax and proper motion that we need to achieve. And there are some requirements on rapid revisits. Basically, we can't just space our observations out every day. We need some observations that are close together on kind of minute timescales so that we can get all the timescales of the time domain science covered. We also have 4 science cases that are going to guide a lot of our scheduler decisions. We want to understand the nature of dark matter and dark energy. We want to catalog the solar system. We want to understand the variable sky, and we want to look at Milky Way structure and formation. For the Rubin Observatory, scheduler is a little bit of a misnomer. Really what we're building for Rubin is more of an artificial intelligence that attempts to make real-time decisions about what to observe. We're not scheduling in the traditional sense. Schedulers usually involve optimization or maximization-like problems. So for example, the Kepler telescope that's there on the upper right, its mission was very narrowly focused on discovering planets in the habitable zone of stars. And so when they were building their scheduler, they wanted to maximize the probability of finding a planet in the habitable zone. It was a very clear maximization. So all their scheduler decisions could be made to maximize that outcome. For Gemini, for example, down there in the lower right, they have a telescope allocation committee. And the Gemini scheduler is kind of trying to optimize that tax happiness by completing the highest rated proposals first and moving on down the line. So we have 4 broad science goals. And I don't know how many supernova equals an asteroid, so we really have a hard time casting Rubin's scheduler as a maximization problem. It really can't be done. We need an artificial intelligence that we can train or tune to make good decisions rather than optimize one single aspect. So to do that, we run simulations. And to run a simulation, we need a model observatory. So our model observatory, we can set it up, we can give it commands like observe this RA in deck, and it will simulate slewing the telescope, opening the shutter, exposing, closing the shutter, and recording the conditions the exposure was taken under. So our model observatory outputs completed observations, and it also outputs what the current conditions at the observatory are. So it will output a map of slew time, how long it will take to slew to any point in the sky, a map of the current seeing, a map of the current sky brightness, when the next moonrise and set is, all the relevant information that we would want to pass to the scheduler. So our model observatory includes kinematic models for the telescope, the dome, and the camera. So we model all those motions. We have a historical weather log. We set our historical weather log so we close anytime the sky is more than 30% cloudy. So that means our weather downtime matches Gemini and SOAR pretty closely, and those are both very near the Rubin site. We have scheduled and unscheduled downtime that's included in the observatory model. We have a log of seeing, of atmospheric seeing. And our sky brightness model is from ESO, plus we've added on a twilight model for twilight time, which we define as any time between the sun at -12 and between -12 and -18 degrees altitude. And there on the lower right, you can see kind of the results of this model. The orange curve shows how much time we would be able to observe if there was never any downtime or clouds. And then the blue curve shows, on average, how many hours per night we get at different times of year. And the shaded regions show when our scheduled downtime occurs. And in addition to this, we also have unscheduled downtime that can occur randomly during the simulation. All right, our sky brightness model includes lots of components: the upper atmosphere, lower atmosphere, air glow, zodiacal light, lunar light, and twilight. And here's a map at a given time of, kind of in RA and deck coordinates, what the sky brightness looks like. And so it's faintest near zenith, and as you get to higher air mass, the sky brightness increases. This is computationally expensive because we have so many components and many of them are in different coordinate systems. It's pretty expensive to compute the sky brightness over the entire sky, especially at time steps of order a minute. So we pre-compute every 15 minutes and then interpolate to get the values, and that seems to be accurate enough and gives us a big speed up when we're running these simulations. All right, so let's look at some of our requirements and how we strive to meet them with our survey strategy. So the image here is the end result of one of our 10-year simulations where I'm showing how many observations there were at every point in the sky. So our first SRD requirement is 18,000 square degrees, and you can see our footprint has this large yellowish green swath that we call the wide, fast, deep area, which is indeed 18,000 square degrees, and we've observed it about 900 times. So we're easily meeting that SRD requirement. Next up, for parallax and proper motion precision is pretty much dominated by how well we observe things in the first year and the 10th year. And so that just means in our surveys, we almost always observe the entire wide, fast, deep region in year 1 and year 10. We can be more creative in the middle years, but in year 1 and year 10, we need to cover the entire sky. For the rapid revisit requirement, here's an image of the LSST field of view, or the Rubin field of view. Ooh, it took me till slide 9 to switch the two. That's impressive. All right. All the little squares there are CCDs, and that inner circle is what we call the science field of view. So we'll get some imagery outside that inner circle, but it's not guaranteed to be science grade. So what we need to do is be able to cover the entire sky and observe any point in the sky. So we use a sky tessellation that's based on a soccer ball. Basically, you have pentagons and hexagons, and as you pack more and more hexagons between your pentagons, you can get finer and finer resolution on how you've tessellated a sphere. And so if we put the center of the Rubin field of view at the center of each of those hexagons and pentagons, we can get something that looks like this. So with 5,292 pointings, we can cover the entire sky. And so most of the sky is covered just once, but there are bits of overlap there. So you can see that pattern where it turns green is where two pointings overlap. If I zoom in on that, here you can see the red arrow in both cases is showing that science field of view. And so when we zoom in on how we're covering the sky, we have most of the sky covered by just the central region, but there is some overlap there. And that's how we're going to meet our rapid revisit requirement. If we tend to observe neighboring pointings, then we'll get that area covered in kind of 30-second to a few minute timescales. All right. Some more motivation is cataloging the solar system and the variable sky. Here's a animated GIF where you can spot a couple moving objects. Those are solar system objects. So to be able to pick those up, we need observations kind of spaced about 20 minutes apart so we can detect that motion. And for variable objects and transients, we would also like color information when those appear. So our main mode of observing is to observe a chunk of sky and then come back 22 minutes later and observe that same chunk in a different filter. And that way we'll be able to both spot the moving solar system objects and get color information on transients. All right. For the nature of dark matter and dark energy, here's the result of one of our baseline 10-year simulations. Now I'm looking at the co-added depth in R-band. And you can see there are 5 deep drilling fields that poke out there, but the wide, fast, deep area is very smooth and uniform because we rotate that tessellation randomly every night. So those overlap regions move from night to night. So after 10 years, we have a very smooth, even final co-added depth. We'll also rotationally dither the camera. So every night the camera will be at a different rotation angle to hopefully randomize any systematics in the optics. All right. So the actual process of how the scheduler makes a decision on where to point on the sky is a decision tree. We've briefly mentioned the deep drilling fields before. They are the top of the decision tree. If there's a deep drilling field up that needs to be observed, that happens. If there aren't any, it falls to the next tier in the tree, which is, can it observe a large contiguous area of sky? And it's not twilight. If it can, it'll observe a large contiguous area of sky. Otherwise, it falls to the third tier, which is just look for the best spot in the sky with a single observation and take it and move on, kind of a greedy algorithm. So what that looks like here is an example night. So on this particular night, all three of those tiers executed at some point. The upper plots show the number of observations in RA deck space. The bottom plots show it in Alt-Az space, where the center of those plots is at zenith. So during this night, you can see on the left a deep drilling sequence executed. So that was 96 observations on a single deep drilling field. And so it's one spot in RA deck, and it tracks in Alt-Az space to make that streak. The middle column is our paired observations. And so there you can see there were several contiguous blobs that were selected and then taken in pairs. That upper middle color bar, you can see it has a minimum of 2. So every spot there was observed at least twice to get those moving solar system objects. And then finally on the right is what executed during twilight time, just kind of spotty observations that stay fairly close together but move around the sky, just filling in parts of the footprint that had maybe fallen behind a little bit. All right, so now I kind of dodged the question of how do we pick those semi-contiguous blobs of sky, because that's our main workhorse engine for observing with Rubin. What we use is a Markov decision process. This is popular in the robotics community, and it lets us balance different factors in weighting where we should look very easily. So our first step is to define the survey footprint we want. And so here it is, the 6 filters, and we use HealPix maps with an N site of 32. So this is 1.8 degree resolution. So this is resolution higher than the Rubin field of view. And so what these maps are saying is that for every one observation in the R band, wide, fast, deep area, we want one observation in I band and maybe 0.4 observations in G, and so on. And we've also got some other regions outside of wide, fast, deep that we're observing a little bit less. So that's our target map. All right, so let me just run the scheduler for a few days, and then we'll pause and look at the basis functions that the Markov decision process uses to define how we select observations. So our first basis function is the survey footprint. So here we've taken the observations that have actually been taken and subtract it from our goal map that we had defined earlier. And I've rotated this so that, again, it's an Alt-Az view. Zenith is at the center. And so you can see there are some regions that have had more observations, and so the basis function there has gone negative. Those parts of that part of the sky is ahead, and there are parts of the sky where the value is positive. Those are parts of the sky of the survey that have fallen behind. And so this is our survey footprint basis function. The next basis function is the 5 sigma limiting depth. So we compute this in each filter. Here I think I'm showing R band. The 5 sigma limited depth is computed from a combination of the sky brightness, the seeing, and the air mass. And obviously those play differently in different filters. And when we compute the basis function, we take the current 5 sigma limiting depth and subtract the ideal 5 sigma limiting depth that point on the sky would have in dark time on the meridian in ideal seeing conditions. So what that means is this 5 sigma limiting depth basis function is essentially the penalty we have for observing a point on the sky now versus waiting for ideal conditions. And so you can see for this, the moon is down in this image. So this is a dark time 5 sigma limiting depth map. And it says, we should mostly be observing along the meridian. If we go to very high air mass, there is about a 1 magnitude penalty for going that far over. These are similar across all the filters when the moon's down. When the moon comes up, it's a much bigger penalty in the bluer filters, and so that will push us to redder filters when the moon comes up. All right, our final major basis function is the slew time basis function. This is just the map of how long it takes to slew to different places on the sky. If we don't slew at all, that's a reward of 0. If we have to slew to the entire other side of the sky, that's a reward of -1, or -1.1 it looks like. There's an annulus structure here that's real because if we do a large altitude change, we need to do a 40-second open optics loop. And so we try to avoid large altitude changes when we're slewing. So to illustrate the basis functions, I like to use this standoff image I got from Wikipedia. The idea is if we put too much weight on any of these basis functions, they will shoot and destroy the other ones. If we are only concerned about image depth, we will march along the meridian and we won't meet our desired footprint. We'll have some downtime, it will throw things off, and we'll have lumps in our final footprint. If we're only concerned about slew time, we tend to just raster at high air mass because those are the shortest possible slews, and we destroy our image depth. So it's all about finding a balance between these three basis functions. Again, we can't cast this as an optimization problem because these are in different coordinate systems and different units. We can't optimize all of these things simultaneously. Some other basis functions we use some masks. We mask the moon, the bright planets, and zenith. We tend to get very long slew times if we go near zenith because the dome has to do a large azimuth slew if we get up there, so we just mask that off completely. We also have a basis function that rewards staying in the same filter because it takes 2 minutes to change the filter on Rubin, so we tend to reward staying in the same filter. All right. Our final reward function is the sum of those basis functions where they've been weighted, and those weights are the free parameters in our AI. And this is what the final reward function looks like in one filter. And you can see there's a nice maximum right there on the east, kind of close to zenith. And by design, we're using smooth functions for our basis functions, and so our final reward function should be fairly smooth. And so what we'll do, once we have this final reward function, we pass it to a decision function which grows the number of heel pixels we want to observe around that maximum, and then maps the heel pixels to the pointings. And again, here's that sky tessellation map, which we randomize each night. So we're going to build up a list, and one of our free parameters is how big a blob should we do. And the blob we select is usually something that we say will take around 22 minutes to execute. And so if I grow that, convert it to pointings, I get something that looks like this. Here's just points of RA and DEC where the decision function has decided it would be a good idea to point. And it's about 35 points, which will take around 22 minutes to execute. If we did it in the order that was by default, it would be a very messy slew. We'd waste a lot of time slewing, so we pass that to a traveling salesman problem solver, which then converts us into a path that looks like this. And then our most common outcome is we will observe this in one filter, change filters, and observe it a second time. And so we'll get our pairs, and we'll get lots of short slews. There are lots of neighboring slews, so we'll have lots of overlap between pointings to get our rapid revisit science. Okay, so the Markov decision process summary. We compute basis functions based on the current conditions and observation history. We compute a reward function, which is the sum of weighted basis functions. And that reward function is 6 heel pixel maps. We pass that reward function to a decision function, which outputs a list of observations to be executed. If we're outside of twilight, we'll do a large continuous block. If we're in twilight, we'll select just the peak, one at a time. Then optionally, something I didn't talk about, we can pass that list of observations to a detailer. We've invented this part. This isn't a canonical part of the Markov decision process, but it lets us modify that list, put it in order for the traveling salesman, add a second pass with another filter, or we can specify the camera rotator angle. So that's where we do those decisions. So there's lots of flexibility in changing the telescope behavior. We can add or subtract basis functions. We can change the weights on the basis functions. We can change the reward function. All of these things are swappable. Some things that sometimes confuse people is that we have no fixed fields. Outside of the deep drilling fields, none of the fields are fixed. So often people talk about, I want to observe this field and then come back 3 nights later and observe it again. We don't track things by fields. That field doesn't exist 3 days later. Another thing is that we're not looking ahead that much. We're not planning days, weeks, or years into the future. We really are deciding at the time, okay, we're going to observe this 40-minute block, do that, and then make a new decision. And we're not worrying about how things will move in the coming days or weeks. And also, there is no master list of observations to execute. Most telescopes have proposals with lists of observations to do. We don't have a list. We just have a final target footprint that we're trying to get to. All right, so let's run the scheduler for 10 years and see what happens. First off, we've seen this footprint before, the number of observations across the sky. We have our wide, fast, deep area. That's the 18,000 square degrees. We have the north ecliptic spur. We're covering this so that we get more solar system objects. We have the galactic plane, the south celestial pole, and our deep drilling fields. There are two more that aren't being pointed out there. We can also look at the pointing history in Alt-Az space. So this is in Alt-Az. Zenith is at the center again. And note this is a log stretch. So we really are highly focused on observing near the meridian. We're not often going to high air mass to chase observations. That on a linear stretch, here's the same plot on a linear stretch. You can see we have to avoid zenith because we can't track through zenith. But other than that, we are doing a very good job staying near the meridian where the image quality and the image depth is the best. Another way to look at the observations that get executed is what we call the hourglass plot. Here we're plotting each night as a vertical line and with the hours from local midnight on the y-axis, and we've color-coded it by what filter the telescope was in. The wavy black line at the bottom is moon phase, and so you can see when the moon is full, we're in Y-band mostly, so that's why we get these periodic red stripes. That's that 5 sigma depth basis function saying, oh, there's the least penalty for observing in Y during bright time. And then the rest of the time you can see it's a very staticky looking color pattern because we're switching between filters and getting pairs in different filters. The white stripes are our downtime and weather downtime, so those are real gaps where the telescope was not taking data. All right, if I look at one point in the sky, we can look at the observing history that happened at that one point. So at RA0 declination -10 degrees, here is the observation history of observations that overlapped that point. And again, I'm looking at time on the x-axis and the 5 sigma limiting depth of each of those observations on the y-axis, color-coded by filter. And so you can see there's a bit of spread there because some of those observations are taken in twilight or full moon, other observations are taken in dark time. It's a mix. You can also see they're clumped together because different parts of the sky have different observing seasons, and so there are seasonal gaps on the observing history there. We can look at the history of that field, or that point, as well by how many observations there were in a night. So on about 100 different nights, that point in the sky was observed once. 175 times it was observed twice, and then 50 times it got 4 observations. And that's, again, because we have this sky tessellation pattern. Most of the time, it'll be in a purple region, in the central region, and we'll observe it twice because we're observing pairs. Sometimes it's in an overlap region, and so it will be that overlap region gets paired, and so that ends up being 4 observations. And sometimes it gets paired twice, and then it'll be 8 observations, and so on. And so here's the distribution of visits per night. All right. Some technical specifications for our simulations. It takes about 6.5 hours to simulate 10 years on a single core. It generates about 2.2 million observations that we record to a SQLite database. We record all the metadata about the observations, the pointing, RA deck, altitude, azimuth, sky brightness, air mass, etc. It's not too tough to install and run if you want to do it yourself. The big hurdle is those pre-computed sky brightness files are 95 gigs for all 10 years, so you need some disk space if you want to run this yourself. Also, the code is the config. We do not have specified config files. It's really, you just have 300 lines of Python that define the scheduler and the simulation. The code is on GitHub if you want to try running it yourself. We've been running on the HIAC cluster at the University of Washington for most of the simulations we've released. All right, so back in 2018, we received about 50 Cadence white papers with ideas of different ways we could try to schedule the telescope and different cadence strategies. The Science Advisory Committee gave us a list of suggested runs, and we've released a few hundred simulations at this point as we've worked through those large lists of ideas. You can see release announcements at community.lsst.org. Simulations have been posted, and our big report detailing all of those simulations that we've run is up at that link if anyone's interested in that. So just to give you an idea, we have other talks that go into detail on our different simulation experiments, but for example, we do different footprints. Here's one where we extend wide, fast, deep north and south and take out the galactic anti-center, give it much less weight. We also do a number of rolling cadence strategies. Here on the left, you can see the baseline after 10 years, and on the bottom at year 3.5 to 4.5, and both of those look very uniform. And then on the right is our rolling cadence, where again we've used a dust map to change the footprint slightly, but the point is after 10 years it looks very smooth, but year 3.5 to 4.5 we have declination bands where we've put a lot of emphasis and some where we have much less emphasis. And so the idea is we'll have very well sampled light curves of transient objects in those dense regions, and then flip that pattern in subsequent years so that after 10 years it adds up to be smooth, but we can have higher and less densely sampled light curves if we desire. We have a lot of different ideas on deep drilling fields. So here's just two examples of our baseline strategy and a strategy proposed by the Dark Energy Science Collaboration, kind of going from gaps of 2 days to gaps of 3 days. And we still have lots of work to do on the deep drilling fields, but we have lots of simulations for different ones. Analyzing the survey performance. Obviously, if we generate 2.2 million observations, it's not trivial to say which pile of 2.2 million observations is better for your science. And so we have written the metrics analysis framework, MAF, to ingest all of this data and kind of do some analyses. And again, we'll have another talk going into detail, but I'll just give some examples here. Here's one of our metrics where we look at the proper motion precision after 10 years. And so you can see the wide, fast, deep has very precise proper motions, and other areas that weren't observed as deeply, the proper motion is not as well defined. We have a metric to look at how many galaxies we expect to observe through various parts of the sky. And here this metric uses a dust map so that dusty areas, we obviously don't detect as many galaxies. We have a metric to look at how many stars we expect to detect across the sky, and we're using the trilegal or GalFast galaxy models. They tend to give similar results, but we can say for different simulations how many stars do we expect to end up in our final catalog. One of my favorites is the Microlensing Metric, where we generate 10,000 microlensing events and then look at the observing history to see how many of those 10,000 we would actually recover. And here you can see the events are not scattered randomly on the sky, they're concentrated on the bulge, LMC, and SMC. And we kind of detect some of them, and as we change the observing strategy, we can detect more or less. We have lots of solar system metrics. We have simulated populations of near-Earth objects, main belt asteroids, Trojans, trans-Neptunian objects, and so we can look at how completely we sample all of those different solar system populations. We're always looking for better survey metrics. We have a Git repo dedicated just to collecting metrics from the community. So if you have an idea, please go to that repo and code up how you'd like to measure surveys. All right. The Rubin scheduler has been worked on by many people over the years, and I would hate to accidentally omit anyone, so I will intentionally omit most people and just focus on student contributions that have been made to the scheduler. Hamna Awan has been working, she's published a paper looking at the dithering pattern and strategies. She's also been a very active member of the Dark Energy Science Collaboration. That was her number of galaxies metric. She wrote that one, and she's been working as a graduate student at Rutgers. Daniel Rothschild, as an undergraduate at Harvard and continuing as a grad student in CS at Berkeley, basically wrote his own scheduler simulation, and we've taken a lot of his ideas and re-implemented it in our structure. But that was a really nice simulation he did. And then finally, Alahi Nahib, as a graduate student at Princeton in operations research, was the one who introduced us to the Markov decision process. And so we've had 3 excellent student-led papers, and they've definitely influenced and made the big jumps in the scheduler that we have today. All right, conclusions. The Rubin scheduler, it relies on a decision tree plus a Markov decision process to dynamically select observations. We've got a model observatory that includes all the important things that we need. We've simulated a huge number of 10-year Rubin surveys and put them out on the web, so if you want to have a say in which strategy you think is superior for your science, we're eager to hear it. We have a tool to help people analyze those outputs. All right, if you have any questions about the scheduler, there are the details of when our PCW session is going to be. Look at that link for the Zoom connection details. And you're always free to start a discussion on community.lsst.org. Feel free to tag me, and I'll be happy to answer any questions you have about the scheduler. Thanks.